All right, welcome to the Explainer. Today, we're going to pull back the curtain on the one thing that truly powers the AI you use every single day. I'm talking about models like GPT, like Gemini. It all comes down to a single concept: self-attention.
Okay, yeah, I know what you're thinking. A formula right at the start, but stick with me here, because this one little line of math, this is where all the magic really happens. It might look kind of scary, but the idea behind it is actually super elegant. Think of it as the blueprint for how an AI truly learns to understand context.
So what is actually going on here, behind all these symbols? Well, it's not just some random abstract math. It's really more like a recipe, a set of instructions for how words in a sentence can literally talk to each other to figure out what the heck they all mean together. It's basically a conversation, just frozen in a formula.
And to understand that conversation, we've got to break it down into three key parts, three roles that every single word, or what we call a token, gets to play. And these roles are the query, the key, and the value, or, just Q, K, and V.
So at its very core, self-attention is just the process that puts those Q's, K's, and V's to work. It's a mechanism that lets each word in a sentence kind of look around at all the other words and ask, hey, who here is actually important to me? This is how the model figures out the weight, or the importance, of every other word, so it can build this really rich, context-aware picture of what's being said.
You can almost think of it like a negotiation for meaning. So imagine one word sends out a query. It's basically asking a question like, okay, I'm a verb, who's doing the action here? Then all the other words present their key, which is like them advertising what they have to offer. A noun might say, hey, I'm a noun, I might be just what you're looking for. And once there's a good match between that query and a key, the relevant word provides its value, which is its actual meaning, its core information, back to the word that asks in the first place.
And here's how that whole conversation gets turned into actual code. So first, the model makes these query, key, and value vectors for every word. It does this by multiplying the input, that's the X, with some special weight matrices that it learns over time. Then, to figure out how well any two words connect, it calculates these scores by multiplying the query of one word with the key of another. Simple enough, right? Then, this thing called a softmax function comes in. It takes all those messy raw scores and cleans them up, turning them into nice, neat percentages, or weights. And finally, the output for our original word is just a weighted mix of all the other words' values. It's a super efficient and scalable system, and it's all built on this foundation of matrix math. Okay, but there's a catch, a pretty big one actually. When a model like GPT is generating text, writing a story or answering a question, it has to do it one word at a time. It can't know what's coming next. So how do we stop it from, cheating and peeking at the future?
I mean, think about it, right? If I ask you to complete the sentence, the weather today is, you can't use the word sunny to help you predict the word is. That wouldn't make any sense, and the model faces the exact same problem. If he could see the whole sentence it's supposed to be creating, it's not really predicting anything, is it? It's just copying. That's not very smart.
So the solution is this really clever trick called masked attention. Sometimes you'll hear it called causal attention. And it's different from what we've been talking about. Standard attention gets to see everything at once, the whole sentence. But this masked version, it forces the model to only look at the words that have already been written. It can see the past and the present, but the future is completely off limits.
And this is how they actually pull it off in the code. They apply a mask to those attention scores we talked about. This function, masked fill, is like a digital blindfold. It goes in and replaces the attention scores for all the future words, the ones it's not supposed to see, with negative infinity. Now you might be wondering, why negative infinity? Well, it's because when you run that through the softmax function we saw earlier, a score of negative infinity becomes a weight of exactly 0. It's the code's way of telling the model, pay absolutely zero attention to these words. It's how we make sure the whole process is step by step and, honest.
All right, so we've got a way for words to find context, and we have a way to make sure it works when generating new text. But language is just so incredibly complex, right? A single conversation between words just isn't going to be enough to capture all the different subtle relationships that are going on.
Relying on just one of these attention mechanisms, what we call a single head, is kind of like trying to understand a really complicated movie, but only watching one character the whole time. Sure, you get their perspective, but you're going to miss all the subplots, all the nuance. You're going to miss the bigger picture, for sure.
So to get that much richer understanding, we use something called multi-head attention.
And this is where it gets really brilliant. You just run that same self-attention process, but you do it multiple times, all in parallel. Each head learns to focus on something different. So, for example, one head might get really good at tracking grammar, subject-verb stuff. Another head might specialize in meaning, figuring out that king is related to queen. And a third one might get good at figuring out what the word it refers to in a super long paragraph. When you put them all together, they build this incredibly detailed, comprehensive view of the text.
And here it is, the whole shebang, the full blueprint, written out as a PyTorch class. Now, don't feel like you have to understand every single line of code here, but just look closely. You can actually see all the pieces we've just talked about. See this? Right here is where it creates the queries, the keys, and the values. And look, down here, there's our mask fill function doing its job, putting on that blindfold. This is the engine, the real core of it all, combining everything into one powerful, multi-perspective machine.
So after all of that, why does any of this actually matter? I mean, why should you really care about queries and keys and all this talk about masks?
Well, it matters because these three powerful ideas, they are the fundamental building blocks of pretty much all modern AI. You've got self-attention, which creates the context. You have masking, which makes creation possible. And you have multi-head attention, which gives it all depth. Put those three things together, and what do you get? You get the core of a transformer. And that's the architecture that powers every large language model you've heard of.
And maybe the most important takeaway is this. What looks like magic, what feels like this totally incomprehensible black box, it isn't. It's actually built on some really elegant and totally understandable mathematical ideas. It's not magic, it's a system. A clever system built from things we've just discussed like matrix multiplications, softmax functions, and that clever masking trick.
So, the next time you use one of these AIs, I hope you'll see it just a little bit differently. Because now, instead of just seeing the final answer, you can appreciate the absolutely incredible, super high-speed conversation that's happening just under the surface. You can picture all those queries and keys and values all negotiating for meaning across all those different parallel dimensions. You've seen the blueprint. Thanks for diving in with me.